with over 25 years of experience in the semiconductor industry. As global books he has published. He holds a PhD degree from University of Southern California, and he has served as a professor at IIT Delhi, and he is he held senior leadership role in Texas Instruments Private Limited. He has been a fellow of INAE and founder of VLSI Design and Test Symposium, which is a very prestigious symposium. So we welcome you, sir. All of us would like to hear from your expertise, and I'm pretty much sure that all our participants will get skilled up because of your resourceful talks. Thank you,
Thank
sir.
you. Thank
Professor
you,
Sahula,
Professor.
I would like to request you to say a few words about this.
I just welcome sir.
Thank you, Vineet.
Sir, I'm sorry that I joined late. Sir. Please.
No, it's
fine. Sir, you may start your screen sharing, and
sure.
Whatever mode you would like to deal with, like interactive or whatever, you please just let us know. Right now, we have not given the access to the attendees for interactive session, but whenever it is like that, you please let us know. We will make them like panelists so that they can. Thank you, sir.
Thank you, ma'am. So first of all, let me thank the organizers, Professor Yadav in particular, and Professor Vineet Sahula for inviting me to be part of this activity. I think EICT is doing an excellent job in organizing these online courses, and very much required today, because it is expected that the semiconductor industry, especially the manufacturing, will take off in India in a big way, right? See, many of you may know that this industry has, I think, the first semiconductor industry that was set up in India was actually a multinational, right? There was some activity in integrated circuit design, etc. earlier also. I can't say that there was no activity whatsoever, but a commercial venture started in 1985. Texas Instruments set up their first, R&D center in India. It was a very small start, but today I think they are close to 2,000 people, right? It's a very large facility now. In fact, it spans across multiple buildings and so on. So the growth over the 40-year period has been phenomenal, right? So initially in India, it started as design services, right? Mostly, the kind of work that was happening in India in the early days was not mainstream design per se, right? There were people who were designing library cells, and in those days, there was no such thing as EDA companies, right? Every company which was involved in VLSI or IC design would develop their own EDA software. It was only in the 90s that we started seeing companies like Synopsys, Cadence, Mentor Graphics, etc., who began to sell, EDA software to all the companies, right? So it began like that, and then slowly it took off in a way that a lot of other companies, especially multinationals, which are housed in US, right? They started setting up shop here. And today, I think I will be surprised if there is some multinational in semiconductor who does not have a office in India. So both Bangalore and I think we also have a very significant presence in Noida, and so these two have emerged as hubs. And I think there are a few other places where you will find some semiconductor activity. Manufacturing is supposed to take off in a big way, right? And test services, right? That has happened in the past few years. So this course is all about testing, right? And so there are companies which offer test services in India. For example, you may have heard of a company called Tesol, which is based in Bangalore. And in fact, there is a full conference now that happens in India, International Test Conference. And they hold the India edition every July. In fact, next week, they are having this conference. And every year, the conference is growing, right? Last year, I think they had several exhibitors offering test services, and the number of attendees is also increasing. So testing is definitely a very big part of the activity, right? So when we talk about testing, actually you should understand that there are two things. See, there is one thing called design for test, right? And then there is something called as test engineering itself, right? So you may have heard already. So I think some classes were already conducted in the morning, and you may have heard what is the motivation for testing and so on, right? Um, so testing is mainly a way to ensure that there is quality in our products, right? So that is what testing is all about. And in order to facilitate testing, the design has to be modified, right? We'll understand why. But the designs that we do today, right, very complex designs, unless there is a structured way to approach testing, it's not going to work, right? It's in the early days, people used to do what is called as ad hoc testing, meaning there used to be what is called as a wall. So let me try and write this out a little bit. So you see, there was the design activity, and then there was the test activity, and of course, in between there is manufacturing. Okay? And there was not much relation between the three activities, right? The design activity was even outsourced, isn't it? So many companies located in India were doing design activity. Manufacturing was happening elsewhere, right? Even today, many of the companies here, for example, Texas Instruments, right? They don't have a manufacturing facility in India. Their manufacturing facilities are located in the US, in China, in Japan, some in Philippines. Um, the reason I think they focused on design in India is because in India they saw a lot of talented engineers, right, who could perform these design activities, and that is the reason why they focused on developing an R&D center here. The same may be true for all the other multinational companies also. Um, so in the early days, designers really did not talk to manufacturing, you know, the fab engineers. So how does design go from the designers to manufacturing? There is a sort of you may have heard of GDS, right? So there is something called the GDS that they have developed. Okay, it's a file format, right? It's called geometrical uh, description system, right? So you remember that masks, right, are required in order to carry on with the manufacturing. So from the design, set of masks will have to be generated, right? And they are used in manufacturing, right? And earlier there was not much, hardly any interaction between these two. So usually the manufacturing, the fab provides certain files to the designers so that they can simulate and verify that this particular circuit will work in this technology, right? So that is the so-called the models, right? The transistor models. That information is given by the manufacturing to the designers, and test happens after manufacturing. Okay, so once the manufacturing is complete, that is when testing really happens. And again, there was hardly much interaction between the design and testing in the early days. But soon, as the complexity of circuits became high, they realized that this doesn't work, right? In fact, I think in the early days it was like this, right? In the timeline, the entire team was busy doing design. Okay? And at some stage, they will do what is called as a tape out, okay? Which means pass on this GDS to the manufacturing team. And that is when, they became free to do the test related stuff. Okay? So they will start worrying about how to test the design only after sending the design out to manufacturing. Okay. So that became a problem, right? Because you may get a design which you can't test, right? You have not thought about how to test the design early, and as a result, you have an untestable situation, right? So as a result, a lot of work was done on what is called design for testability. They realized that you can't really ignore these two. I mean, you can't separate these two very well, right? And similarly, now it is accepted that even these two cannot be separated, right? So there is a lot of dialogue happening between design and manufacturing, right? So you may have also heard of a term called design for manufacturing. Okay, so you also hear about DFM, right? So in this class, we are mainly focusing on the test aspect, right? And we'll understand why a structured approach to testing is really required, right? So there are many reasons for testing integrated circuits, right? One of them is quality, as I mentioned earlier. Okay. So what does it mean? See, if I make a large number of chips on a wafer, right? So this may be my wafer. Okay. See, unfortunately, not all of them will turn out to be good chips, right? There may be what are called as manufacturing defects in them. Okay, some of them will have. Okay, the point is we don't know which ones they are, right? And when we have to ship the products to the customer, we have to ship only the ones which we understand are good parts. Right? Willingly, we should not provide bad parts to the customers, right? So, if a there are two or three terms that we define here. One is known as the yield. Okay, that is a percentage of chips that actually can be sold to the customers for profit, right? As a fraction of so it is a number of chips which can be sold, which are good, divided by the number of chips manufactured. So yield is, a high manufacturing yield is required for us to be profitable, right? And the reason, like I said, why some chips are not good enough is because they have certain defects inside them, manufacturing defects, right? And when the customer receives the chips, right, there is a term called as DPM. It stands for defective parts per million. Meaning, see, suppose a customer purchases 1 million chips from a company and finds that some 100 of them were defective, right? The question is, why did the company sell defective chips in the first place, right? It's not that they wanted to cheat. Okay, it's not that the company wants to cheat somebody and therefore, also adds a few defective ones or something like that. That is not the point. The point is the company may not be able to clearly distinguish good from the bad. There is no sort of a easy way to tell a good chip from a bad chip, right? Mainly because the complexity of the chips is very high, and we have a limited amount of time for testing, right? So these two are like totally diagonally opposite things. The complexity is growing, right? Which means we have to give a lot more time for testing, right? On the other hand, due to intense competition and so on, everybody wants to go to the market as early as possible, right? So there is time pressure to release the product to the market, and at the same time, the complexity of the chips is growing. So when we do some testing, right, there is something called as fault coverage. See, suppose you look at the example of you know let us say a flight is about to take off, right? So a team of engineers may visit and make certain observations before the flight takes off to see whether it is fit enough to fly, right? Now, if you think about it, the number of things that can go wrong in a flight will be very large, isn't it? It's a very these modern aircrafts are very complex machines, right? So if you try to go into all the nitty-gritty details and say, look, so many different things can go wrong, and I want to make tests for all of them, it will take too long, and your flight may not be able to take off in time, right? So they decide that these are the only things that we care about. So they will write down a few things, right? And say, look, let us check whether this problem is there, this problem is there. So there may be a few such things that we can, okay. So this is the so-called fault model. Okay, so these are the faults that we are willing to model. Okay. Does it mean that this is adequate? Not really, right? So in the same way, when a semiconductor company wants to test a particular chip, they have a fault model that they have to work with, right? And as you can see, if you make a very complicated fault model, huge number of faults in that model, then making testing for all of these will be very expensive. It will take a long time. Okay, I think many of your faculty members also, right? So you understand this very well, right? See, in your curriculum, you may have taught for like 40 hours or something like that, and you may have covered a lot of concepts, right? Now, can you make a test which covers everything that you have taught, right? Unfortunately, test will be too long. It may take many hours for the student to attempt such a test. So you really cannot afford to do that, right? You have only like 2 hours to test the student, maybe 2 to 3 hours, right? So you will sort of, in your mind, you may have a fault model and say, do you think the student knows about Kana maps, right? Does the student know about, let us say, De Morgan's laws? So you will have a few such items that you have written down. You may not explicitly write it down, but in the back of your mind, you have that so-called fault model. If the student doesn't know Kana map minimization, then he will he will score less, right? He will score less in the test, right? So in the same way, the company will need a fault model, right? And going back to the analogy of the test that faculty members conduct for their students, what does it mean if let us look at this square here. See, let us say the the student passes the test and the student passes. The other is student is good and the student is not. When I say good, that means he or she is worthy of passing. Here it means the student is not worthy of passing, right? So this is a happy situation. The student is good and oh, I'm sorry, student is good and he passes is a happy situation, right? But if this happens, it's terrible, right? Student is good, but this uh, he failed his class. He failed the exam, right? Even this is not such a good thing, right? I mean, the student is not good, but he made it in the examination. And this, of course, is okay. I mean, it's not something to celebrate, but a student who is not good is also, not declared as a pass, right? So these are the two problem situations, right? One is the student is good, but we ended up failing him. And similarly, the student is not good, but we ended up passing him. Now, if you think about why this might happen is we did not test enough, right? We had a 2 hour limitation on the test, and that student just got lucky, right? He had prepared for only, let us say, out of 8 chapters, the student only prepared for maybe 4 chapters. But many of the questions that he or she got, enabled him or her to pass the examination, right? And we declared that the student is a pass, but actually the student is not worthy of passing, right? So this is a problem, right? So when the company sells a million chips, there may be a few such defective chips which will pass our tests, and they will, such a thing is called as a test escape. They will escape our test, right? And they reach the hands of the customer, right? And in fact, they may even get into the system. See, this customers, they're in a hurry to move on with the product design, right? So they will possibly, introduce the chips into their PCBs, and the PCBs will get further integrated into a system, right? And unfortunately, what will happen is the at some stage, some of those devices will fail, right? The customer's customer may report that there was a problem, and then when you go and understand what the problem is, it may turn out that the chip is the one which is defective. If, for example, today chips are used everywhere, right? We use them in automotives, in biomedical applications, industrial. So there may be a robot that doesn't work correctly. There may be some automotive, some car that doesn't, work correctly or something like that. And those are all very dangerous things, right? And then when an investigation is made, right, then there may be a sort of a law suit kind of a situation, right? So DPM is a way for a semiconductor company to sort of protect itself by saying, look, I can only guarantee that certain percentage of these chips are good, and the remaining they may be defective, right? And the number of that DPM could be something like 100 or 200, right? So the smaller this value, the more expensive those chips will be, right? Think about it. If you have to guarantee to the customer saying that not more than a certain small fraction of your chips will be, defective, is a big thing, right? It's a big commitment, and as a result, there will be a, you know, signed, agreement between the two companies, the buyer and the seller, that the DPM will be some number like 100 or 200 in a million. So it's 100 in a million. And this 100 to 200 is okay when you're talking about maybe, things like chips that are used in maybe your television or your mobile phone and things like that. Because, nobody is going to have any serious problem if they don't function correctly. But if your car has a chip like that, or if a nuclear power plant has a chip like that, or a space vehicle has a chip like that, or a medical implant has a chip like that, there will be very serious repercussions, right? So as a result, there is more and more push for lower DPM, right? So these are now for automotive, etc. They are like one digit or something like that, right? So one digit numbers, right? So that is something that you need to understand, right? So when chips go bad, right? And let us say those faulty chips are defective chips are have reached the customer. The customer may end up recalling the product, right? So like for example, there may be a situation like you may have heard about some practical examples of this also, right? I mean, there may have been incidents where the fault of the car was accelerating, right? Toyota example, I think, is very famous, right? Even without anybody pressing the pedal, right? There was acceleration in the car, right? So that can be a very dangerous thing, right? So in that situation, what will the automotive company do? See, they don't know what the problem is, right? If they know that it is a semiconductor chip, they may be able to do something about it. But when they don't know what the reason is, they may end up recalling cars, right? That can be very, very expensive, right? The other reason why testing is done is, see, even though we may have sold the chips, right? The chips are sold here, let us say, right? And at that time, they were all good, right? All these 1 million chips that I sold, right? Let us pretend that all the 1 million were good, right? But when these chips are actually put to use in practice, right? They will, ultimately fail. All chips will ultimately fail in a certain number of years, right? So that is why there is a what is called as a lifetime, right? No semiconductor vendor will say that it will work forever, right? There is some lifetime. It may be 5 years, it may be 3 years, it may be whatever number of years, right? So the warranty is only given for a certain number of years because all these chips go through aging phenomena. They are subjected to a lot of stress, right, throughout their usage. There are temperature stresses that these chips go through. There are voltage stresses that they go through, and their operating conditions may not be very, there may not be a lot of noise in the surrounding, right? As a result, the package may fail, right? Mechanical stresses. So many reasons why chips may fail even after they were good. They were good here when I sold them. So no semiconductor manufacturer will want their chips to fail in this period because there is a warranty, right? If the chip gets returned here saying that your chip failed during between this time, then there is a contract, right, between the two parties that a new semiconductor will have to be supplied, right? Or there may be even stronger clauses. Say, I'm just giving an example where you just replace the part, right? But it may not be so simple. It may be a much more, many more difficult clauses may be there, right? Because we are confident. See, the semiconductor manufacturer is confident that it will work for 5 years. But if it fails within that period, there may be a much bigger penalty to pay or something like that, right? So there are many such phenomenon, right? Uh, so I will talk a little bit about these failure mechanisms later, right? Then there are also some. See, there are two kinds of defects that we talk about. Some are catastrophic faults where nothing can be done about it, right? If a chip has that catastrophic fault, we can't really do anything about it. We have to throw it away, right? But there may be situations where repair is possible, right? And there may be situations where the defects are not permanent, right? They come and go, right? So both these situations could be there, and you may have noticed this also. Sometimes your laptop suddenly gets stuck. It doesn't respond, right? And then if you reboot, things seem to be okay again, right? Now, what really happened? Why did it fail? Is it a software bug that caused it to hang, or was it a some other hardware intermittent fault that caused it to hang? See, that is difficult to say, right? But hardware also can say face these intermittent faults, right? So these are the things that we need to understand, right? So testing is something that you know um, people have traditionally, or if you go back and understand, everybody gets excited about design, right? Because wow, I mean, I can design this microprocessor, I can do this, I can do that. So design is very everybody's favorite, right? But without testing, there'll be no quality, right? There'll be no reliability, and as a result, your customers may not even come to you, right? So testing is a very essential aspect about a chip, right? So don't ignore it, right? So this is a completely different ball game testing, and there are dedicated engineers for the testing, and also something called as design for test, right? So those who enter DFT or testing, usually, they continue in that domain for many years. Okay. So this is a completely different role. Okay. So test engineering and so test engineers typically work at the fab, right? Test engineers typically work at the fab. They have a very close relation with the fab. They are actually responsible for working with the so-called automatic test equipment. See, there is something called as ATE, okay, which stands for automated test equipment. And the test engineers are the ones who understand how to use these test equipment and how to automate the flow of testing and things like that, right? Whereas there are also people who are part of the design team and working on how to enable the test engineers in doing their work very efficiently, right? So those are the DFT engineers, right? I hope that point is clear. There are what are called as DFT engineers who are part of the design team, right? And there are test engineers who are, I won't say they are part of the manufacturing team, but they usually sit, close to the manufacturing site, right? And they are the ones who operate the test equipment. I won't say operate. Usually, all this is automated, right? But they are the ones who develop the test programs, right? And are responsible for the final, quality check, right? So let me talk a little bit about, I think you may have already spoken about in the morning. I think Professor Virendra Singh may have spoken to you, and he may have mentioned to you about different fault models, right? So there are many fault models, right? Uh, so one of them is the Stuckett fault model. I think uh, Vineet, was this discussed? All this Stuckett faults were discussed.
Somewhat, Dr. Menka also have discussed preliminarily.
Okay, okay.
Menka.
See, there is such a thing as a Stuckett fault, right? And uh, first of all, let me sort of clarify what is meant by defect and what is meant by Stuckett fault. What is meant by fault, right? These are two different terms. So there is
Yes,
something called as
hello, sir. A brief
ah,
overview of the faults we have given in the morning. It was given by Professor uh, Singh also, and I have started stacket faults in the morning. So I used
okay, all right.
stacket fault,
Good, good.
equivalence and dominance based collapsing. I completed, so.
Right, right. Very good. So defects and faults are two different things, right? So this picture may bring that out, right? See, this is a defect, right? See, when you let us say lay out a, circuit on the screen, right? Layout editors you may use, etc. And they look very, perfect. These are perfect rectangles, etc. Right? And you may have followed all the design rules, right? In spite of it, when you actually manufacture, right, there may be these kind of faults that may, the defects that may still remain, right? So this is an example of a particular kind of fault known as a bridge fault, right? See, what could happen is you have a metal line and another metal line running very close, right? So there is usually some sort of a rule which says that there should be a separation of so many nanometers between the two wires, right? But despite that, right, sometimes something like this may actually happen, right? And when these carry large currents, okay, there are large high density currents that go through these metal lines. What could happen is there is something called as EM that happens, electromigration, right? Electromigration. It's something like, when you have, let us say, imagine that there is a, dust particles, in settled somewhere, right? And if a large wind flow, goes through, many of these dust particles will sort of go here and there, right? Something like this will also happen in a metal, right? I mean, there is a large current and the metal ions will tend to get displaced, and continuous usage for years together may result in ultimately a crack developing in the in the metal line, right? So slowly that metal may become open, right? And where do you think the metal that is getting dislodged from this wire, where will they go, right? Imagine that were to happen here, right? Slowly this thing will close, right? And it will ultimately become a bridge fault, right? So a bridge fault is another type of fault. You have already been told about stucked faults, right? So the other type of fault is called bridge fault. right? So today, people want to test for a number of fault models, such as single structured fault models. These are called single structured fault models, and then bridge fault models, and then there is also something called as the delay fault models, right? You may have heard about those also. So there are delay fault models also. And because of the kind of markets that semiconductors are now getting into, automotives and so on. In addition to these, there are people are also talking about cell-aware testing, right? So many other, okay, cell-aware testing. So these are all new fault models that people want to. So what does it mean? It means that as the complexity has grown, right, the number of faults that we have to test for has also grown, right? So let us quickly maybe do an exercise, right, so that so let me get a feel for the class, right? So you may have already done this, so I want to get a feel. So let me pretend that these are A, B, C, D. So let us look at these single structured faults. Okay. So as far as single structured faults are concerned, see, there is a sort of a theorem which says that it is enough to test for all the primary inputs and the fan out branches. So if we refer to this as E1 and E2, right? Then the fault list will consist of A0, which means A stuck at 0, A1, which means A stuck at 1, B0, B1, then C0, C1, then D0, D1, and then E1, 0 and E1. And E2, 0 and E2. So these are our, this is our single structured fault model. You may further be able to eliminate a few of them. For example, E1, 0 is same as A0, right? So you may be able to remove this E1, 0 from your list because you can't tell them apart, right? Whether E1 is stuck at 0 or A is stuck at 0, the circuit behaves the same. So as a result, they are equivalent, right? In the same way, E2 stuck at 0 and D stuck at 0, you may be able to consider that they are equivalent and you may want to strike this off, right? So you may be able to do a little bit more compaction, right? And finally, as come to this list of faults, right? And similarly, you may want to come to a list of bridge faults. See, unfortunately, bridge faults may be quite a few. A and B may be bridged, or B and C could be bridged. A and D could be. So if there are n wires, right? In principle, every wire could be bridged with every other wire, right? So that is very large number, right? It's a n times n minus 1 by 2 or something like that, right? If there are n wires, the number of bridge faults can be very large, right? So this is too big because n will be in the order of several millions, and as a result, bridge faults can be too many. So what they will do is they will look at the actual layout, right, and see whether these are feasible or not. See, maybe A and let us say the output, the chance of them bridging may be very low because they are far apart in the layout, right? So you may have to come up with the bridge fault model. You may have to wait until your layout is done. If you don't want to wait till then, your number of faults will be very large, right? You will have to. So, and there are two kinds of bridge faults, right? One is called the AND bridge, and the other is called as OR bridge, right? If, for example, what happens when there is a bridge fault between two such wires, right? Imagine that I have put a 0 here on this wire, right? So as a result, this NAND gate is, is supposed to go to 1, right? And imagine that I have placed a 0 on B also, because of which this guy is high. And I have placed a 1 on this guy, right? And as a result, this is tending to become 0, right? Now, when there is a bridge between the two, what will really happen, right? Depends on the relative, strengths of the transistors used in these NAND gates, right? So together they may both become 1, right? Or both become 0, right? If they tend to become, both of them tend to get pulled up to 1. This guy is strong and he pulls this guy also to 1. So we have an OR bridge, right? So it's like an OR gate connected between the two, and 1 OR with 0 is a 1. So that 1 is going to reach this guy, right? A good circuit will get a 0 here, but a faulty circuit will get a 1 here, and as a result, it will produce a 0, right? Whereas a good circuit will produce a 1, right? So that is an OR bridge. It could also be that there is an AND bridge that can happen between the two. That means the 0 is strong, and this 0 will pull both the wires to 0. And as a result, in this example, there is no way to tell apart, right? The good circuit will also produce a 1, and the AND bridge will also produce a 1, right? So for the AND bridge circuit here, it may not be possible to have a test vector at all, right? So this is what bridge faults are, right? And then we also talk about what are called as path delay faults. So these are speed faults. Okay, there is nothing wrong in the circuit per se, right? Except that some of the gates have higher delay than expected. Right? See, the gate delay depends on many things like the you know the transistor parameters, right? It may depend on the voltage that is applied, right? So there are many factors that influence the delay, and you can expect, right, that although we try to lay out all the NAND gates in the same way, right? All of them are copies of the same NAND cell and so on. There'll be some, variation in their widths and lengths and so on, right? So all of them will not be identical. So there will be some statistical variation of the width and the length, and there'll also be statistical variation in the thickness of the oxide, right? And even the power that reaches these gates may be slightly different. So all that, when we consume together, it may mean that, some of these are having higher delays, right, than expected, right? So when we do the so-called timing analysis, right, we would have done the analysis of the critical path. Okay, let us assume that this path is considered the critical path, has the longest delay, right? And we would have adjusted the clock to sort of, to take care of this critical path delay, right? But if, let us say, it turns out that, this has a slightly higher delay and this also has a slightly higher delay, etc. It may be possible that there is a violation. Okay, there is a setup delay violation that will happen, causing the circuit to fail. Right. So this is a timing failure. Right? So we assume that the circuit will work correctly at a certain speed, maybe 100 megahertz. Right. But when we do the speed testing, right, it turns out that it doesn't pass at 100 megahertz. But if you are willing to operate it at a slightly lower frequency, then it may pass. Right? So that is also not good from a profit point of view, because the customers will pay high price for high speed chips, right? Whereas if if it is not working at 100 megahertz, you may not be able to charge the customer the same amount of money. So usually they will bin the chips into many speed bins, right? So maybe this is 100 megahertz. Everything passes at 100 megahertz. Some of them may pass at 110 megahertz, right? And some of them may pass at 90 megahertz, and some of them may pass at maybe 80 megahertz. And maybe less than that is something that you don't really care about, right? If your chips are passing at less than 80 megahertz, maybe there is no market for them whatsoever, right? Whereas people are still willing to buy maybe at a lower price all these chips, right? So this is additional. So this is also something that test engineers have to do, right? I remember I mentioned to you about test engineers. So one of the roles that they also play is called speed binning, right? So although nobody likes test because it costs money, right? I mean, the reason people are afraid of test is because it is very expensive to do, right? But you have to think about the value it provides. If you are not able to give the DPM that the customers want, right, then your customers may go away, right? You will lose the market. So that is definitely one reason to do testing. That is to preserve the quality and build the brand, right? If your chips are not, if let us say you build up a bad brand, saying the company's chips, don't work, they fail, etc., right? Then that will do a lot more damage to your reputation and to your market than anything. So as a result, test is very important to keep that quality high, and test also is important in this example. Test can also save some money for you, right? Instead of throwing away the chip entirely because it fails to meet the speed requirement, you may be able to sort of come up with these speed bins and recover some of the costs by selling these chips at a lower you know cost than the premium cost. Okay, is it all making sense? Anybody has any questions? I have been speaking for a long time, so would like to go and understand if there are any questions at this point of time. Any questions here?
Yes, if you have questions, please write in the chat box. We will take the questions from there. If you have any questions, please write in the chat box.
Voice is not clear. Nivedita Joshi, voice is not clear. Are you able to hear?
Voice is clear. You may recheck your device. You may reconnect your device. Voice is clear. We have given the YouTube channel also. You can, if you are not able to check it from here, you can check from there also. It's clear, no problem.
Oh, fine. All right. So I
Those who
hope.
have any question may feel free to type in the chat box. We will take the questions. Sir, if you want a 5-10 minutes break, we can have the break.
No. I don't need a break. I just want to make sure that they are following whatever I'm saying.
Okay, sir. Thank you, sir. Please.
Oh, there is something that fellow has asked, even in E2 path. Uh, See, even in E2 are called fan-out branches. Okay, even in E2 are called fan-out branches. What I meant is when you talk about single stacked faults, you must consider all the faults at the primary inputs and all the faults at the fan-out branches. So A0, A1, those are the stacked faults at A. B0, B1 are the stacked faults at B, etc. Then it is enough to consider E1 0, E1 1, E2 0, E2 1. The E0, E1 and the stacked faults here, etc., they will turn out to be either equivalent or dominant, and we don't have to look at those at all. Is that clear? Pankaj or somebody asked that question. Is that clear, Pankaj? Dr. Aditya, somebody asked. Aditya Mandloy. Is that clear, doctor? You removed E1 0, E2 0. Yeah, E1 0 is equivalent to A0. See, if I have an AND gate, let me see, suppose we have an AND gate, right? See, if you don't do
You can ask a question by unmuting yourself.
yes,
Okay. Thank you, ma'am.
see, there is a stuck at 0 fault, there is a stuck at 1 fault. There is a stuck at 0 fault, there is a stuck at 1 fault. There is a stuck at 0 and a stuck at 1 fault. So these are the complete list of faults for a NAND gate, right? But if you think about it, if A is stuck at 0, right, then the output of the NAND gate will be 1, right? The effective behavior of the NAND gate changes, right? And the output becomes stuck at 1. In the same way, if B is stuck at 0, the output becomes 1, right? So there is no way to tell them apart, right? Whether I inject A0 as a fault or inject B0 as a fault, the output will always be the same, right? As a result, we say A0 is equivalent to B0. Okay. In my previous example, A0 and E1 0 are equivalent. I cannot tell them apart. Is that clear, Professor?
Yes, sir. One of my questions, sir.
Huh.
Uh, Sir, you have discussed the path delay fault, and
Yeah.
you have discussed the critical path for the finding the
Hmm,
most
hmm,
weak.
hmm, hmm.
Sir, my question is means how to mitigate it. Means anyhow there is a delay in a fast means a very fast system in
Hmm.
megahertz range digital system. So how can we just find the fault where is the fault and what are the
See, okay. See, the point is that is not the problem of testing, right? See, the testing problem is not to diagnose what is wrong. Okay. We are only here to pass or fail the check. You understand, no? The job of testing is not to figure out what is wrong, right? So there are two terms that we use. One is testing. And the other is diagnosis. Okay. By applying a test, right? Let us say we are able to we have figured out that there are some certain number of tests. Okay, there are tests T1, T2, T3, etc. And we may know which one is passing. This is passing, this is passing, and then T31 is failing, and so on. So we may have this information with us. If all the tests are passing, then of course the chip is a good chip. We say it's passed, right? But when some tests fail, right, we are in a hurry. Remember, the test engineers are dealing with millions of chips. You understand? There is no time for them to stop and say, let us figure out what is the wrong with this chip or anything like that. They will just make a list of, I mean, they will separate these bad parts. They will go to another department where they may receive all these bad chips and try to figure out what could be going wrong. Okay, that is a different thing altogether, right? It's very difficult to figure out in your example, what is the path which is failing and all those kind of things, right? That will require things like maybe even removing the package that with acids you can expose the layers and then you can look at them under the microscope, figure out. So that is a very different thing altogether. Okay, this class is not about diagnosis. Is that clear, Professor? There are very few people who do that. Okay, it's a
Oh,
very
yes, sir.
small job sector, right? Very few people in a big company will be involved in diagnosis, but testing is a much larger activity. Any other questions? Periyasamy, your voice is clear. Okay. Anything else? Sai Kumar? Okay. All right. Let's move on. So I was talking to you about path delay faults, but what can happen in the path delay fault is also the same thing. The number of paths that we have to worry about may be very large, right? See, look at this particular circuit here, right? See, if I look at the number of paths, see, here is a path from input to output. Here is another one, and here is a third one. Then there is a fourth one, and so I can see from A there is one path, from B there are two paths, from C there are two paths, and from D there is one path. So there are that many paths. So in general, right, there could be circuits where the number of paths can be exponential in the number of inputs, right? And when the number of inputs, see, in modern circuits, even the number of inputs is very large, right? It may be in the order of several hundreds. And imagine an exponential number like 2 to the power n, where n is like in the order of 100 or something like that. See, that is humongous. You can't possibly cover all the paths, right? So path delay fault testing is hard to practice, right? On the other hand, what people do is they try to look at what is called as transition delay fault, right? What is a transition delay fault? See, there we assume that each gate has a fault. See, for example, here is a gate, right? Let us call this output as F. Okay. We assume that the entire fault is concentrated here. Okay. Nobody else has a fault. Only F has a slow to rise fault, or F has a slow to fall fault, right? So nobody else has a fault. You understand? Just like the single circuit faults. See, in single circuit faults, we assume that there is only one wire in the circuit, like in this example, A0, right? Everybody else is good. Only A is stuck at it. Okay. Now you can ask yourself, is that even possible? Right? How can a defect cause only A to become 0? Right? In general, the multiple things can fail at the same time. No, there is absolutely no doubt about that. So we argue that if you have done a good job of testing for single circuit faults, you have also caught a lot of multiple circuit faults, right? So multiple circuit faults are impossible to deal with. There is exponential number of multiple circuit faults. So we just cannot deal with them, right? So we only deal with the single circuit faults. In the same way, path delays are too many in number. So we look at only individual wires like A, F, etc., and say, hey, something is causing this wire to become too slow to rise or too slow to fall, right? So in this example, there will be only at E, there may be a slow to rise or a slow to fall fault. and at F, at G and H. So there will be only 8 faults that we have to deal, right? So that is a much reasonable number of faults. So those are called transition delay faults, right? So let me mention that here. We have transition delay faults. Just like stuck at 0 and stuck at 1, we have slow to rise and slow to fall. So these are the faults. Any questions about this? So far you must, I hope everybody understood what is the difference between testing and diagnosis, right? I hope everybody understood that testing cannot prove that the chip is good, right? It's only a limited amount of tests that we can apply. So if all the tests pass, it doesn't mean anything. It doesn't mean that there are no defects in the chip. There is still a possibility that there is a defect in the chip. It's just that we have not had a chance to, sort of expose it, right? So there is a little bit of a, possibility of a what is called as a test escape, right? Meaning that there is still a fault that we had not factored into our fault model, and that caused this particular problem, right? So I hope everybody has possibly you have been already meant they have possibly talked to you about fault coverage already, right? So what is fault coverage? Everybody anybody wants to tell me what is fault coverage? What is fault coverage? Somebody is asking me to explain bridge fault. Bridge fault means two wires which are not supposed to be shorted or getting shorted. That's all, right? There are two wires. These are not supposed to be connected, but in the layout, these wires were running very close to one another, possibly. And as I showed you, there is a possibility of them getting connected inadvertently. Okay, is that clear? Sai Kumar. Sai Kumar. Let me ask you guys. Okay, let me test your understanding. Right? What is and? Okay. See, if there is an OR bridge between these two faults, it's as though there is a fictitious OR gate here. Okay. So this circuit is behaving like this. So this is the actual circuit, right? But this bridge caused a fictitious OR gate to appear between. Is that clear? Similarly, a bridge and bridge is when a fictitious AND gate appears between. Okay. See, today morning, I'm sure they told you about the definition of a test vector, right? When do we say a vector is a test vector? If it can tell the good and the bad apart. So if I apply some values to A, B, C, D, right? This is a good circuit. What is a good circuit? It does this. It's hard to say. BC bar and A bar and then BC bar, D whole bar, right? And that whole bar. Okay. So this is a good circuit. But a bad circuit will behave like this, okay, which is what BC bar dot A whole bar plus BC bar dot D whole bar, okay, and that whole thing bar. Okay. So some combination of A, B, C, D will make them produce different outputs. Okay, this F and F prime will produce different values for some combination of A, B, and C. Okay. So you may be able to tell me that answer, right? So let us do this exercise right now. So this is a good circuit. See, if a fictitious OR gate were to appear between the two, right? See, if you want to expose a bridge fault, I hope everybody appreciates that we should push the values to opposite values, right? If you send them both to 0 or both to 1, you have not even activated the fault, right? So we have to make them different. See, for example, let us say we apply a 0 here, and as a result, this becomes a 1. A good circuit will have a 1. And let us say we want to make this 0. So working backwards, let us say this is 1, and let us say 0, and this is x. Okay. So this is a test vector 0, 0, x1. Okay. A good circuit will produce a 1 here, and it produces 0. And a good circuit will produce a 1. Now suppose there is an OR bridge between the two, then as you can see, the fictitious OR will end up producing a 1 on both these inputs, right? And as a result, the faulty circuit will produce a 0. So 0, 0, x1 is a test vector for whatever this line is. I think I had called it F and G. Okay. So let us call this wire F. Let us call this wire G. So we say F bridge with G. Okay. For that 0, 0, x1 is a test vector. 0, x0 will all 0, x0, 1 also will detect. Okay. So 0, x also is okay. Is that clear? Somebody who asked, Sai Kumar, is that clear? You will realize that here AND bridge you will not be able to detect. Okay, AND bridge you cannot detect. All right, shall we move? Okay. Sai Kumar, I suggest you read about it online. You will find plenty of literature on this, right? So you please understand. If I apply 0, 0, 0, 0 x 0 1 or 0, 0 x1, a good circuit will produce a 1. You have to convince yourself that that is correct. And if there is an orbit between the two, the faulty circuit will produce a 0. So that is all we want. We want the good and the faulty circuit to behave differently, right? All right. Anything else? Fine. So as you may have realized now, testing is a very there are many aspects to testing, right? There is the fault model that we talked about, right? And see, there is one more thing that I think I may have to mention, that is people talk about maybe this was mentioned too in the morning, but I'm not sure. So there is something called as functional testing. And there is something called as structural testing. If it was mentioned in the morning, somebody should be able to tell me what they are. Can anybody tell me? Okay. So maybe I'll tell you. See, when you get your circuit back, right? When you get your circuit back from manufacturing, right? You only have access to the primary inputs and you only have access to the primary outputs. Okay. So you can apply any values you want on these, right? So you can control these wires. So we say this are controllable and these can be observed. Right? You can take a multimeter or you can use an oscilloscope or something like that to measure the outputs at this point. And similarly, you can control these values to any point. There are a vast majority of wires which are inside which you cannot directly control or observe. Right? And that is really the difficulty, right? We cannot directly observe those wires. We have to indirectly observe them at the primary outputs and indirectly control them through primary inputs, right? So when you get your circuit back from the manufacturing, suppose you have to do, suppose you ask yourself, what is the functionality of the circuit, right? If you say, look, it's a microprocessor, right? And then you say, hey, let me check if it is behaving like a microprocessor, right? And then if you start constructing the tests, right, that is called as functional testing, okay? Where you go by the functionality of the circuit and then try to understand, whether it is doing what it is supposed to do. And as you can guess, that is how the people used to do in the early days, right? I told you about these ad hoc tests that people do, right? That is what it was all about. They were doing functional testing. The good thing about it is, you don't have to do anything to the design. The design remains unaltered. We try to argue about, hey, if this function, if there was no defect, this should have behaved like this. But now, okay, for example, let us take a microprocessor, right? Suppose there is a function, there is a, something called as move, let us say A, comma B. See, everybody knows this from your Intel 8085 or something like that, right? You may know what it does. It transfers the contents of A to B, okay? So there will be somewhere a decoder which is useful in transferring the contents of A to the bus, and then so A should put the value on the bus, and we should transfer the content to B. Okay. Now to select A and B, there will be some decoder, right? What if that guy has a fault, right? So instead of enabling A, it may enable multiple registers, right? While move A, comma B is done, maybe A and C contents are both on the bus. And as a result, some garbage gets into B. Similarly, maybe when trying to copy to B, maybe there are multiple registers which are enabled, and as a result, A will not only go to B, but it will also go to many other registers. Right? So how do you test whether move A, comma B works? Right? You have to first initialize the registers to some known values, right? Maybe all the registers are initialized to 0. Then A is initialized to some FF or something like that. Then move A to B. Then actually see whether which registers are impacted. Is it only B which was impacted? So you can see that even such a small instruction if you have to go and test, it will take you a lot of instructions, right? A lot of work is required just to test for one instruction. And not only that, nowadays there are so many instructions, right? The microprocessors are very complicated now, right? They have a lot of instructions. Each instruction has so many addressing modes, right? And there are so many registers, right? And in the registers, maybe, some bits are bad, right? It's not that the whole register is bad, but maybe, some particular bit in the register is bad. We don't know, right? So unfortunately, if you decide to copy FF to 0 B, it might go through. But if you try to copy some other pattern like 5 5, it may not work, right? So you can also see a lot of different kinds of data may have to be moved in order to see whether. So that is the problem of functional testing. Did you understand functional testing, guys? Is everybody clear about functional testing? So the idea is you have got your microprocessor back from the and then you are trying to make sure that there are no problems, right? And it is very hard thing to do. The good thing is you don't need to know what is inside. I don't know when I'm applying functional tests, nobody needs to tell me how the microprocessor is designed, right? So this can be useful in the user testing. See, when somebody buys a microprocessor, right? If I buy a microprocessor from Intel, right? Intel is not going to tell me what logic they have put inside their ALU or anything like that, right? They will not tell me all those things. I have to go by the function. They will give me a data sheet which says, this is how the microprocessor behaves, right? If you are willing to use the data sheet and develop some tests, right, that is okay with you. That is user testing. So long ago, that is how even manufacturers used to test based on functionality. But I think even maybe uh, almost 35 years ago, they started realizing that this is not going to work, right? So they moved to structural testing. Structural testing can only be done at the manufacturer's end because it requires you to know what is inside. You need to know how the circuit was constructed. Like in this, say, I need to tell you this, okay, that these are the gates, okay. So with the information about this, then you can argue about, fault model and single circuit fault model, bridge fault model. Whereas in functional testing, see, the fault model is very abstract. Okay, the fault model may be um, the transfer from A to B does not happen correctly. So that is an abstract kind of a fault model, right? And then you develop a test for that. And it is practiced, maybe very limited amount of functional testing is still done, right? But most of the testing now is structural testing. Is that clear? So all your single circuit faults, bridge fault, etc., they're all structural tests. Is that clear to everybody? All right. So I'm sure you guys learned about combinational tests, right? You may have heard about. So there are two types of circuits that we usually deal with. One is combinational, and the other is sequential, right? Any useful circuit will be a sequential circuit, right? We rarely use, the kind of systems that people build today. They'll all be having, memories and flip flops, etc. So it is. Combinational circuits are maybe only used in certain building blocks. That's all, right? So it's really sequential testing that we need to worry, right? So sequential circuits sort of take on this form, right? I mean, there is a primary input, there is a primary output, and then there are flip flops, or the memory elements. So this is how. So this is our previous state, and this is our next state. So this is our sequential machine. This is a very simple model of a sequential machine. So these may be called Q1, Q0 or something like that. Q0, Q1, Q2. And these are D0, D1, D2. Right? Now the thing is, it's easy if we can talk about combinational testing, right? So if we can cut off these wires like this, right? And if we had full access to these wires, right? So if I could get full controllability to these wires, and if you could get full observability to these wires, then my testing is, I can do it in a very reasonable way, right? Because this is a combinational logic. Okay? And there are good number of, people have worked on this combinational logic for a long time, right? We know how to generate tests for these, etc. Right? So going back, let us quickly understand. Let us take the example of a combinational logic circuit, the same circuit that I have been using. Let us say I want to test for stuck at one fault here. Okay. So what is the way to test for it? Anybody wants to help me here? So this is A, B, C, D. This is E. This is E1. This is E2. This is F. This is G. So tell me how to test for a stuck at one fault here. See, if a stuck at one fault were to exist there, right, then the circuit will behave in a slightly different way, right? This circuit behavior will, what will happen is this is one, so A bar will come here. So we are generating A bar, and this is what? BC whole bar, and that is BC whole bar dot D bar dot F bar versus the actual circuit. So we must find some input combination which will make the two functionalities different, right? So we have to first, there are two aspects. One is called as fault activation. Okay, we have to activate this fault. So if we are worried about E stuck at one fault here, we have to put the value 0 on this somehow. Okay. So when I put a 0 on this, then a good circuit will have a 0, but a faulty circuit will have a 1. Unfortunately, I cannot see if how do I put a 0 here. I can put 1 on this. Okay. If I make B equal to 1 and C equal to 1, I can activate. A good circuit will have a 0, a faulty circuit have a 1. So I am able to differentiate between the good and the bad. But the problem is I can't observe this point. At this point, E1 is not a primary output. I had to somehow make it, visible here. The effect of this must be visible here. So what value should I put at A in order to push the effect of the fault to this next line? So what should I do? Somebody is answering something. Jatin Khatiyar, stuck at A1, we provide 0 and sensitization path. Yeah, I mean, see, if you put a 0 on this wire, see, it will, both the good and the faulty circuit will produce a 1. That is not what we want, right? So put 1 here. Okay. So that will cause a good circuit to produce what? What will a good circuit produce here? A good circuit sees a 1 and a 0. So it will produce, yeah, some Sai Kumar is answering. Correct, Sai Kumar. Whereas a faulty circuit will produce the opposite value, right? It sees 1, 1 as the input, so it will produce a 0, right? Now, you see, I hope everybody understood that a stuck-at fault here is not the same as stuck-at fault here. Okay? If E1 is stuck at 1, it doesn't mean E2 is stuck at 1. These are two different branches, right? So it's okay to assume that we can put a different value here, right? So in order to push this further, I'll have to apply what should I apply here in order to push the output, the fault to the next point? If I put a 0 here, unfortunately, both the good and the faulty circuit will produce a 1. What should I put here? I have to put a 1. Then a good circuit will produce a 0. A faulty circuit will produce a 1. Right? Now, how to put a 1 here? We can maybe do it by putting a 0. So 1, 1, 1, 0 is a test vector for E1 stuck-at. Because if there was no fault in the circuit, right, then this will produce a 0, and as a result, both of these will produce a 1, and the output here will be 0. But if there was a stuck-at 1 fault here, this will produce a 0, and the output will become 1. Okay. So is that clear to everybody? Why 1, 1, 1, 0 is a test vector for E1 stuck-at 1? So the method of generating test patterns for single stuck-at faults is, if there is a stuck-at V fault that we are looking at, somehow make this into V bar, okay, by applying suitable inputs at the primary input, get the opposite value to come at that wire. That is supposed to activate the fault. If you cannot activate the fault, then you can't test for it. Then after activating the fault, you have to propagate the fault to one of the primary outputs. Okay. There may be many ways to propagate it. Choose any one of them and make the effect of the fault appear at one of the primary outputs. Okay. So there are two aspects: sensitization or path activation, fault activation. Some people call it a sensitization also. The other is propagation. Okay. So you see, if I give you a very large circuit like this with millions of gates, right? And there is one point here, and I'm trying to apply, test it for a stuck-at 0 fault. Then I'm saying, what will cause it to make it 1? Okay. What will cause a 1 to appear in this wire? And I may have many inputs here. There may be n inputs. And unfortunately, that is a hard problem, right? Can I find a, can I find a combination of inputs which causes a 1 to appear on one of these wires, right? So that is it is not a there is no in computer science they have these polynomial time algorithms, right? And they have these NP complete problems, right? So this problem doesn't have a polynomial time algorithm. Okay. So traditionally, what people do is they use backtracking, right? And when we do backtracking, there is a good chance that we may go through all the input combinations in the worst case, right? So n, see, there are 2 to the power n possible vectors, right? And who knows, none of them may be able to develop a one at their own. I hope everybody appreciates that. A circuit may be built in such a way that none of the vectors can put a one here, right? So if that happens, right, then there is no test for this particular structure zero fault, right? And we spent an enormous amount of time looking at all the 2 to the power n combinations only to realize that there is no fault, there is no test, right? So, uh, like I said, people use backtracking. And what they will do is, since n in the practical circuits will be in hundreds, right? So you can imagine 2 to the power n is going to be really large, right? Normally, this doesn't take so much time. Normally, for most faults, it may just happen very quickly, right? Very quickly, you will be able to send a 1 or a 0 on that particular wire, right? See here, we didn't struggle too much, right? We just argued that this can be done by setting B and C to 1. Like that, most circuits are well behaved, right? But there may be some circuits which are, especially which have a lot of XOR gates, right? And a lot of, convergent fan outs and things like that. See, there it can so happen that, it may take a long time for the tool to figure out how to even cause the fault to be activated. Right? And then after that, you have to further propagate the output, right? So as a result, you can, have a situation where it is taking too long, right? So what people will do is the tools generally they say that we will have a time limit, right? So the number of backtracks that you can do on one particular fault will be limited. So you can set that count to 100 or whatever that number is, right? So the higher that number, the longer the tool is likely to take, right? So you can let us say start by whatever the default number is, let us say 100, right? And when you run the tool, right, remember there's a big fault list, right? It has a big list of faults. It will pick, and let us say you have asked it to generate a test vector for one of these, right? And it may not be successful in generating a test in that given time limit, right? The number of backtracks equal to 100, right? Then it will do what is called as, it will say, sorry, I can't, find a fault. I'm sorry, right? It will drop it, right? So what can happen is, with all good intentions, you are trying to test, right? So this is your big list of faults. See, you can imagine that now the number of wires in the circuit is of the order of millions, right? So this is in millions. So it's very difficult to sort of go test one by one all the million. So what they will typically do is they will use initially some random patterns. So they will start with some random patterns, right? And these random patterns may actually test a number of these faults. Okay, so usually, almost 60 to 70% may be caught by random. Whatever remains, okay, those are the faults which I cannot test using random pattern. Okay, so if you plot, so let us go back to the same circuit. See here there are 16 patterns. Okay. So can one of you give me a random pattern? Just give me a random pattern. Okay, Sai Kumar has given me 1101. 110. Okay. So what will a good circuit produce for 10? It will produce a 1. Okay. And a good circuit will produce a 0. And a good circuit will produce a 0. And a good circuit will produce a 0. So what will cause the output to change? What faults will cause the output to change? In other words, when I apply 1101, a good circuit is producing a 1. Which faults will cause it to change? Okay. See, unfortunately, the output H stuck at 0 will be caught, but it is not in our fault list, right? Remember, our fault list is only what are the fault lists? A0, A1, A0, A1, B0, B1. Then what was the other one? C0, C1, D0, D1. And then E1, 0, E1, 1, E2, 0, E2. These are the only faults that are in our fault list. Okay. Even among these, I think we argued that E1, 0 can be removed because it is equivalent to A0. And what was the other one? E2, 0 also we can. So we only are looking at these faults. Will any one of these cause? See, if A is stuck at 0, what will happen? If A is stuck at 0, this will become 1, right? But unfortunately, nothing will change because this other guy is holding the 0 value. Okay. So A0 is not caught by this particular vector. B1 is definitely not caught because it is not even sensitized. Because B1, we have put a 1 here, so B1. Similarly, B0, it will not work because this is already 0, right? So this is not caught. A1 is not caught because it is not even sensitized. C0 is not caught. C is not sensitized. C1, let us see. If C1 were to exist, then this will become 0. This is the only one that is caught. C1 will be caught. Everybody is convinced on this? C1 will be caught. Because if this fault exists, then the output here will become 0, and both of these will become 1, and as a result, output will change to 0. Okay. So this random pattern 1101 detected C1. D0, let us see. I don't think so. It won't get caught because if D is 0, this will become 1, but this guy is holding 0. Okay. So even 1, it's not even sensitized. E21 is also not sensitized. So it's rather sorry. This particular test catches only one fault. Like this, if you try a few random patterns, right, you will realize that, as you increase the number of random patterns, you will start getting slightly better and better coverage, right? In our case, there are only how many faults? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 faults. We are looking at 10 faults, right? And we may get, suppose I take 5 such patterns. Who knows? I may get some out of 10. Let us say I end up getting 6 of them. Okay, so the 60% is caught. In this case, unfortunately, there are not many test patterns. There are only 16 patterns, right? So in the worst case, I can apply all of them and I will get coverage, right? But in a large circuit, right, I can't afford to do that, right? I can only apply, nobody will allow me to apply so many patterns, right? It will take too long. So 60%, after that, it tends to sort of level off. Then it's very difficult to, work beyond this, right? So the first thing to do in testing is to apply some random patterns and get a reasonable amount of coverage, and then use an actual tool. Okay, we are left with some faults which could not be covered by random patterns, and we are trying to focus on those. Is that clear? Anybody has? So, Dr. Aditya, you can try the 0101 pattern yourself and tell me what tests what for. So this is an exercise for everybody. So here's an exercise. Find the faults caught by one was, we already did the example of 1101. Let us try 0101, 1111, 0110. So try these 3 and see how many patterns, how many faults they detect, right? So the point is, after having done random testing, right? Now we are trying to catch the remaining faults by targeted ATPG. ATPG stands for automatic test pattern generation. So some people also call it as ATG, automatic test generation, right? So there are tools which will read the netlist, that gate level circuit, and they will do the hard work of coming up with this fault list for single circuit faults, and then through random patterns they will go ahead and get some coverage, right? And they will give you that option, how many random patterns do you want me to apply, right? And then whatever was not caught, they will go and try to target those, right? And like I said, sometimes they may not work at all. They just fail to give a uh, they may not get a test at all, right? So there are, at the end, the ATPG will tell you that there are some testable. I was able to test these. So these were okay. Then I could not, I had to drop some of these faults. And some it will tell you that there is no way, some are untestable. Okay. Meaning that nobody can get a test vector for this. Right? So even maybe you already know this, but I will repeat it anyway, right? Anybody knows why there will be some faults which are untestable? Okay. So let us consider an example. Let us take this circuit. Is there a test for A stuck at 0? Is there a test for A stuck at 0? What should I apply at A in order to activate the fault?
Sir, we have to apply 1.
Correct. We have to apply 1 so that we can activate the fault. But what happens when I apply 1? It will activate the fault. But that
No,
1
sir.
will come in. That
Uh,
1 will come and, unfortunately, we will not be able to propagate the fault. You understand me?
Yes, sir.
So A stuck at 0 cannot be tested in this example. Is that clear to everybody? And the reason why it is happening is the circuit has redundancy, right? See, what it is doing is A plus A bar B. Okay. So we are testing A, this is A, and this is A bar B. So A plus A bar B is what is being, but this is actually, we can simplify it to A plus B. If they had realized it like this, then A stuck at 0, we could have tested. Right? But if somebody introduces some redundancy like this, then some faults will not be tested. So this is not the fault of the, see, the ATPG tool should be careful. If it doesn't realize that this redundancy is there and tries to generate a test vector for this, right? It may work very hard only to find out that it is not testable. Right? In this example, there are only 2 inputs, so it may not be such a big deal. But imagine there is a very large combination circuit with hundreds of inputs, and there is some redundancy like this, and the ATPG tool is really trying hard to, find a test and failing, right? So usually they go and do a analysis and try to, see whether there is a problem like this. Okay. So they will also come back and tell you that there are such situations, right? So we may have in a very large circuit, right? A very large circuit, we can classify the faults into, testable. Hopefully, that's a big, large number, testable. Then there are some faults which are untestable. And then there are some faults which are dropped. Okay. So these, you can try to do something about them by increasing the time limit and trying to run, right? Generally, the requirement for a circuit is that, it will have a high stuck at fault coverage. It may be like 98% or something like that, right? So to achieve that, sometimes it is impossible in the way the circuit is currently designed, right? Maybe we are able to get 88%. Okay. What we are actually getting is only 88%. Then the remaining 10%, what do we do? How do we get that coverage? Right? So that is what the DFT engineers have to work out, right? They have to understand why the report that the test tool will maybe give you some clues as to what is going on. Why am I not getting that? So if there is untestability, etc., they have to figure out, right? See, unfortunately, they should not go and try to meddle with the circuit, right? That will not be correct. They are DFT engineers, right? Their role is not to fix anything in the circuit, right? We cannot question. In this example, we cannot go and argue with the design engineer that, why have you given A plus A bar B? You should have given me A plus B, etc. We can't say that. There may be some reason why he has designed it like that, right? Redundancies are introduced for various reasons, right? there are fault-tolerant circuits which have built-in redundancy, right? You can't go and say, it's making my life hard as a test. I can't find out test, so you go and remove all the redundancy. You can't say that, right? So that is one thing all of you have to understand. Test engineers or DFT engineers, you can add some additional circuitry, right? That is allowed. You can request the design engineers to modify the circuit and add some extra, circuits for you. But you cannot go and argue that, you please redesign this site. This is not working or something like that. That is not allowed. Okay. So that is the challenge in front of. And this is not only for, this is single circuit fault. In the same way, there is a coverage goal for even your bridge faults, even your transition delay faults, right? So they have to work hard in order to make sure that all these goals are met. Any doubts here so far? Did you understand?
Yes, sir.
All right. So today what we have looked at is we have understood some of the. How much time do I still have? Am I done, Professor Manju, Menaka?
Yes, sir. The time was till 8 o'clock.
Hmm.
So it's up to you, sir.
No, I'm saying let us understand. Are there any questions before we break for the day?
So, do you have any questions? We can unmute you if somebody is having any questions. If any of the participant, Dr. Sagar, you are unmuted. You may ask question.
Yes, yes, sir. You have told about ATPG, automatic test pattern generator.
Hmm.
So it is an external device used to test the circuit. So how the combination can be selected in the auto means it can generate or we can give the test sequences to test the circuit.
No, first of all, it is not an external. See, it is a software tool. Okay, ATPG is a software tool. Okay, so what is its role? Read the structure of the circuit. So what are the gates? How are they connected? Then come up with the fault list. Then, like I said, apply some random patterns and see how the fault list gets impacted, right? So many of the fault list will possibly become smaller. Then whatever is left, we try to target. So, for example, if I have a big circuit and there is a particular fault that I could not test using random patterns, let us say it's a stuck at zero fault. Now the ATPG tool will try to find a test pattern which will cause it to activate the fault and then propagate it to one of the primary outputs. Okay. So this is a directed test pattern generation. Okay. It is an intelligent. Random patterns is not intelligent. It is just throwing some random patterns and seeing what they can do for me, right? But here it is trying to be intelligent and figure out how to test this fault, right?
Okay,
So
sir.
once
But
it finds, ah,
my concern is that I have built one ATPG software tool,
hmm,
but it can test a 16-bit multiplexer at the same time 16-bit adder. So means
mhm.
how it can distinguish? It has some lookup table or directly it can by
It
software
doesn't care
analysis.
about the functionality. See, that is what I was trying to tell you.
Okay,
ATPG
okay,
doesn't know about the functionality. It is just a bunch of gates, that's all. Right?
okay, okay, sir.
Whether it
Okay,
is a multiplier, multiplexer, decoder, whatever it is, doesn't know. It only knows that, oh, I have to put a one here because I have to activate the fault, right? I'm trying to activate a stuck at 0 fault, so I have to put a 1. What can I do to put a 1? Work backwards. This is an NAND gate, right? So one way to
Okay.
put a 1 here is 0, 0 or 0, 1 or 1, 0, right? So it will try to take one of those. It will take a decision. Let me try 0, 1. Then it will go work backwards, right? While doing so, it may come across, what is called as a conflict, right? Then it will say, oh, that didn't work out. Let me try a different one, 1, 0, right? So that is called backtracking, right?
Okay.
Backtracking is a way by which we, sort of try to take local decisions, and at some point that decision may contradict or reverse our decisions. And many times we are successful, right? Many times you may have done things like maze routing, right? Say, for example, as children, you may have all played that maze routing, isn't it? Famous
Yes,
maze
sir.
routing. There is a big maze of some kind. And there may be walls here and there where you cannot enter, etc. And you have to somehow go from point A to point B, right? And then you try to see, sometimes you will get a block, then you reverse and then you try another path. Sooner or later you will all get, right. So that is the same thing. The ATPG tool is trying to be like that, back the same backtracking that is used in
Okay,
maze
understand.
routing. Yeah. What else? Any questions?
No, sir. Fine, sir.
Hmm. See, somebody asked me whether there are any tools. There are many tools which are available from commercial vendors like EDA. These EDA vendors. One is Synopsys. They have an ATPG tool, right? It was called Tetramax earlier, but I don't know whether they have changed the name. Then similarly, Cadence, they call it Modus. And then there is Tessent, or it is part of, it used to be called Mentor at one point. Now they call themselves Tessent. So they all have tools for ATPG, right? So if your organization has access to these tools, you will be able to practice ATPG tools. Unfortunately, in the public domain, DFT tools are not really available, right? You do find tools for many other things, but there is no. Uh, I cannot recommend any tool for ATPG at the public domain level. Okay. What else? Any other questions? So I should mention here that there is another thing called as fault simulation, right? That is a reverse thing. See, ATPG is given a fault, find a test. The reverse is given a test, tell me what faults it can detect. See, we did that here. We argued that 1101 can cause C1 to be caught. So that is nothing but fault simulation. We just did a fault simulation of this test vector 1101 and argued that it can. So what ATPG tool will do is, suppose it, finally found out these are the lists of faults that I need to target. It will pick one of them and find a test vector. And then it will do a fault simulation and see whether it can detect any others, right? And then drop them, right? And then it will keep, so target any one, fault and find a test. Then fault simulate. Then update the fault list. And then repeat. Keep doing this till you can remove all the list from the till your fault list becomes empty. Okay. Or you run into situations where you simply cannot find such a test vector because you are running out of time, and then you abort the fault. These are called aborted faults. Okay. Dropping and aborting are same. Okay. Some people call it as drop fault, some people call it as aborted fault. Aborted fault means I could not find a test vector for that fault in the reasonable amount of time. Any questions here? So all of you should know terms like what does structural testing mean? What does functional testing mean? What does fault simulation mean? What does single circuit faults, bridge faults, transition delay faults? Okay, so we introduced a lot of terminology, right? And we talked about combinational testing. I'm sure you'll go through some algorithms for combinational testing, etc., right? And maybe sequential also. So in our next class, which is I think day after tomorrow, we'll get into a little bit more about some of the logic based and things like that. Any
So,
questions before we? Go ahead. Go ahead.
yeah, so if there are no questions, can we conclude for the day? Participants, do you have more questions? Yes, sir, please.
All right. Thank you. I'll see you day after
So,
tomorrow.
thank you so much, sir, for a very
Thank you very much.
insightful talk. And really, it was very insightful to all of our participants. They have enthusiastically participated. And yeah, we would like to hear you from you in the upcoming sessions also, sir. Thank you so much, sir.
Okay. Thank
Thank
you.
you, sir. Thank you very much.
Okay. Yes.